by the end of the week.
Okay.
Lab submission is by the end of the week. So if you go to the Moodle, you'll find that there is already a link. Where is Moodle? Here is it. So there is already a link for the lab submission. I think there are some few students who have taken with me previously, just very few who have taken with me Jupe 3000, earthquake and seismology. The lab is a bit similar, but why I'm giving it to you again? The reason being the Jupe 3000 course, it's an elective course, will not be offered, will not be given next semester. Offered only once in 2 years or once in 3 years. And I thought the material, the lab, which was given in that course is good. It's worth for you to do it. So let's go back to the slides and try to complete seismology part. Our emphasis for today is what's Snell's law and how we can use Snell's law to trace the wave from one layer to another layer. I believe we have completed all of these parts. We have made discussions on the three component seismograms, and we said why we need three component seismogram in the same station. A station is a geophysical location where we put a seismograph. Seismograph is anything which can record seismic waves. It can be geophones, it can be seismometers, Anwar or Anwar. So seismic station is anything which can have a seismogram, a seismograph. And seismograph is actually an equipment which can record seismic waves or seismic energies, whereas seismogram is the record itself. The record nowadays are actually in digital formats. Let me just make some few tweaking in here. Oh, that's fine. So nowadays, actually, everything is digital, but in 1950s, they were right away written on papers, as you see here. Digital formats were not available or very expensive, so there was simply a pen which was writing on papers right away in real time. But nowadays, everything is digitized, and even the way we save this data, they have been standardized. The way we record the data and save them, I mean, by standardization, is making a similar format. So geophysicists from different parts of the world, they can read or understand how to read this data. For example, one of the simplest format to save seismic data is SIGY, SEGY. If I write it in somewhere here, don't need to know these things, but SEGY. But SEG is a society. It's a very well-known society called Society of Exploration Geophysicists. And they made this standardization, so everybody, when they save geophysical data, they save them in this format. So if I know how to read this format, I can read easily seismic data and display them in computers. Earthquake data, actually, they saved not in SIGY, in different format. So seismogram is the record itself. Long time ago, they were displayed on papers in front of you in real paper. Nowadays, everything is displayed in computer monitors. It's easy, so you can manipulate them, you can change them, you can scale them differently. This is a benefit. Anything in computer, you have it in digital format, and the numbers are saved, the values are saved in actual numbers. And when I have them, I can display them in different ways. However, anything on a paper, real paper, it's just printed out and you cannot make changes. What's actually the benefits of having, back to the slides, what's the benefits of having three components rather than one component in a single station is, first of all, know the direction of the wave and also know what's the type of the wave. Am I recording P wave, S wave, or surface waves? Surface waves that we know as the one we only here in our course discussed are Rayleigh and Love waves. We said Rayleigh wave is the most destructive wave. It's causing the most damage during an earthquake. And one condition when we deploy the station or deploy these sensors or place them or manufacture them, we try to make them orthogonal. Whenever I say orthogonal, the terminology defines that those three components are actually perpendicular to each other. And what you see here is actually a real seismogram. This seismogram is a record of a real earthquake. So this is how it's recorded. The first arrival, the first thing you see or notice is P wave. And how you say that this is the first arrival? How I define that this is that part here exactly is the first arrival. I know because anything earlier than this time is quiet. There is nothing. There is no deflection. There is no shaking. It's straight line. And this is what we name the onset, the beginning of P wave. That's where the P wave arrived. And after some time, the S wave arrived. And later, we'll see the surface wave are arriving. The first surface wave is a love wave, and then we have the Rayleigh wave. So this is probably love wave, and later on after that time, we have the Rayleigh wave. Some characteristics of these waves, as we discussed earlier, P wave and S wave, we call them body waves, and they have high frequency content, but low amplitude. The amplitude is low. The energy contained within P and S wave is lower than the energy contained in surface waves. Energy is proportional to the amplitude usually. The higher the amplitude, the more the energy the wave contains. Another characteristic is actually, yeah, that's the frequency. So we have surface waves are having lower frequencies. In digital formats, usually we display things in this manner. So it's in this manner. So what I see, that's a time. In earthquake sense, I keep always recording because I don't have the control when I record. We need to differentiate what is actually a man-made and what's made naturally. Earthquakes are natural phenomena. We don't have control on them. We can't expect when they happen. It's hard to make expectations when they happen, the earthquakes. So we keep recording. We always keep recording. We are recording huge amount of time. Actually, most of the computers work, almost like 30% of the work worldwide of computers is dedicated to geophysical analysis, to geophysical processing. Whenever you go like in a conference, geoscience conference, you'll find big computer companies are there too, like Dell, like HP, showing their workstations, high computer workstation. Why? Because geological modeling, uh, simulation, petroleum engineering, forecasting, history matching in petroleum engineering, also seismic data processing in geophysics, they require a lot of processing. You need very strong or powerful computers to make things easy. Otherwise, you spend days and days. Your computer is doing the same job. You keep waiting for the job to finish. So almost 30% 25% of the computer power worldwide is used uh, in oil industry in general, or in geophysics and geological and petroleum engineering studies. Nowadays, there is a shift toward toward something which is consuming a lot of power. Almost, I believe, 20%, 30% of the energy of electricity worldwide is used or dedicated toward that thing. Who can tell me what is the thing I'm talking about? It has seen a boost. It has seen a really high boost nowadays. It consumes a lot of power. Let's see who is for.
Doctor, what do we call the from a surface wave arrival in
What we get.
seismogram?
What's your question again,
After
Mohammed?
surface arrival,
That's
after surface wave.
aftershock. Yes, this is an aftershock. It happens actually.
No,
The
between
reason
30 and 60.
30 and 60. This is whole surface wave. This all of it is surface wave. Wave is not single just peak. No, it's a train of wave. It's a train within like some minutes to keep vibrating, vibrating, and vibrating till it dies out. So the question what's this? In geophysics, we name it CUDA. So this is P wave CUDA. From here up to here, that's the P wave CUDA. This is S wave CUDA. And whenever you do some analysis on P wave, you don't take a line, you take usually some time span from here to here. So my PhD was taking like 20 milliseconds to make P wave analysis and S wave analysis within 20 or 50 milliseconds. But I'm using like oil industry data. The earthquake data is usually different. There is good separation between P and S wave in earthquake data. Why is that? Because the wave traveled long distance, whereas in my case, I was using something called microseismic. The distance from the source to the receiver is very short. P wave is traveling faster, S wave is following up, but there was not long distance to make segregation between them. But if there is long distance, and let's say two cars, one is traveling at a speed of 1 kilometer per second, the other one is traveling at speed of 80 kilometer per second. What is the difference in time when they travel from, let's say, Muscat, from Khoda to Al Ma'bela? Very small difference. Yeah, one is faster than other, but small difference. But let's say, what's the difference in time if they travel from Skiu to Dubai or to Salalah? So the time difference then is large. Again, that's a PCUDA. Again, back to my question, what's the thing which is consuming a lot of electricity power nowadays is what we call mining, what we call cryptocurrency mining, Bitcoin mining, or other currency mining. That clear? So let's move
Victor, you
along.
mean large in between two waves?
Did you say again, Muhammad? What's your question?
You mean the large in waves? If the distance is large?
I couldn't hear you very well. I'm sorry. There is some kind of noise. The voice wasn't clear too. Or
I mean, Victor, you said from Muscat to Salalah. It is large. What is the large here?
the distance is large. The distance is very large compared to the distance from Skiu to Al Ma'bela.
So the wave will be clear or what? You mean?
The wave,
Here
if
is
you are
large.
if you are hammering
Seismogram.
by, yeah, if you are hammering, actually, if you are using a hammer, the wave is not clear. The energy will not travel that much. But if the wave is generated actually by an earthquake, a large earthquake, it certainly will reach Salalah. The seismic stations there will record it. That's my idea. So this is when I say the time S minus P, the time of S minus P, that's the time difference between P and S, going to be larger the larger the distance. Let's assume that there is a big earthquake. I recorded it, the earthquake happened, la samahallah, nearby Oman. And Oman stations, they recorded. This S minus P, why I take S? Because S is usually larger. S takes longer time to arrive, so the number is larger number. I need a positive difference, so it's there is no possibility that P arrives later. P always arrives earlier than S. So the
So, Doctor,
larger the
we use
distance.
it, we measure the distance to find the center of earthquake.
Yes, we measure. That's the lab today. We'll come to the lab later on. So let me complete these things. And I think I even completed this part. So we'll use, nowadays we are using such type of instruments, especially in geophones. So this is a geophone. The only difference that there is a spike, a mesmar, and we dig the spike to the ground when we do the recording. And this is the inertia of mass. That's the inertia, which is the thing which keep moving. The magnet is the inertia. The magnet keeps moving whenever there is a shaking, whenever there is a movement. And the movement is converted to a voltage. That's what we record. And we save it. There is something you would like to explain slightly. Whenever we are recording, yani, computer cannot, there is no computer which can record or save data continuously. Everything in computer is digitized in digital format. So there is a terminology in computer called sampling. يعني, let's say my waveform is coming like continuous waveform, and this is time. This is the amplitude, that's the time. And this is amplitude. So I say, what is the amplitude at that time? You say that's the much, and I say, what's the amplitude on this time? Time 1, time 2. You can say that's the amplitude. You can go and read it. But then I say, what's the amplitude in the middle? You can go and say, oh, that's it. But what's the amplitude in here? You say that's it. But you cannot go indefinitely. And a computer cannot, otherwise you will run out of storage. There is no number you can settle. Yani I can divide, keep dividing. The mid of 0 to 1 is half. The mid of 0 to point half is quarter, and so on. There is no middle. So you need to set up some sampling. You decide how much I sample. I sample every 1 second, every 2 seconds, or every millisecond, or every microsecond. That's what you decide during the acquisition time. So these things, when they record them as an analog continuous waveform, but they're going to be digitized. They're going to be sampled. You are recording them into your computers as in a sampled format. We'll not go to detail into sampling because this is going to be discussed in another course called geophysical data processing or signal processing. We'll discuss also what is the ray and what's wavefront. Wavefront is actually what happens in reality. Whenever there is a detonation of a charge or an explosion, the energy travels in every direction. And if I'm in homogeneous medium, If I'm totally in homogeneous medium, the wavefronts are always spheres. They go up in all direction as a sphere. That's the point, and keep expanding, uh, equal in every direction. But if it's not homogeneous, the velocity here is faster than the velocity here, so it expands faster in here than here. It expands faster in this area because the velocity in this area is faster. The expansion here going to be faster than the expansion in the upper direction because the velocity probably is lower. So we cannot make the always the assumption that the wavefronts, those wavefronts are spherical. They can change direction. And that's what we call something anisotropy. But you don't care about anisotropy for the time being. We care about what's wavefront and what is ray. Ray is actually an imagination of thing. It's not a real thing. We just make an assumption that there are rays moving in a certain direction. The ray direction is actually the similar to the wave propagation direction. And they are, when we draw them, we try to make them perpendicular to the wave direction or wavefront directions. Again, to the same slide, I think I even discussed this one. If the Earth is uniform, it's made of one single velocity. Whenever I say uniform, I mean the property, the physical property is not changing with direction. Uniformity means the physical property is the same in every direction. Anisotropy is the opposite of uniformity. Anisotropy is actually the similar terminology as heterogeneity. Anisotropic or heterogeneous medium is the opposite of a uniform medium. If the Earth is uniform, the velocity is the same in every direction. There is no change of velocity, just single one value velocity. The wave travels from here to here is equal to the wave travels from here to here, from here to here, and finally from here to here. Why is that? Because all these distances are the same. These distances are all the same. It's also applicable to this case. The only difference, the distance have been increased. And there is something we call epicentral distance. In geophysics, something epicentral distance, the point is at the radius or at the radius of the what's it, epicenter, they call it, or point of the circle, the middle point of the circle. This is what we call epicentral angle. This is how it's measured. This could be 120 probably. I'm not sure how much exactly it is, but this is an epicentral distance. All of these, they have all of these arcs, they have the same epicentral distance. So the travel time, the time it takes for the wave to travel from A to B or A to any other point is the same because the velocity is the same and the epicentral is the same. But that's actually not true because we know the Earth is the velocity of the waves in Earth are increasing usually with depth. Earth is made up of different layers. Each layer has its own velocity. There is something called spherical symmetry. And if the assumption we have that the Earth is eccentric, made up of different layers, is similar to an onion, you can peel apart the onion shells, you'll find the onion is made up of different shells or different layers. And if we run, for example, a seismic experiment, making a big explosion here and trying to record the time it takes for the wave to travel from here up to the opposite side of the Earth, is the same as this one. Is the same as this travel time from here to here is the same as this travel time from here to here in general, in large scale. And that's true actually. And most of the models they created, velocity models, the geophysicists created for the Earth are 1D model. 1D يعني it's changing only with depth. It's not changing with horizontally, spatially. It's the velocity is increasing with depth. And up to now, most of the location algorithms locating how to locate earthquake, you recorded the time. How I get the distance then? I need the velocity. I need the velocity. The velocity models they brought actually are 1D velocities. So when they recorded a lot of earthquakes, because there were a lot of stations around the world, they found that the observed time, that's the distance, this is one distance, another distance, and so on. And each distance gives you a travel time. This is the time for A, for example, this is the time for B, and that's the time for C. And when they made a continuous line through all of these points, they found that the line is a curved line. What this suggests? This suggests that the velocity is increasing actually with depth. The deeper you go, the velocity is increasing usually. And the Earth is not uniform. It's not made up of one single layer. If it's uniform, we would have observed this linear trend. The travel times would have been linear. But the real one, the one we are observing, is curved actually. And this is how they actually made it, because they have earthquake, they know where the earthquake happened exactly, and they keep recording the time, travel times of P, the first onset of P, the first peak or trough of P, which is actually, I showed you one just right now, this one, which is time scale. So we come to the point how we can trace the waves, the rays, how they propagate through the earth. They follow a law, they follow a principle, which is called Snell's law. So whenever there is a boundary between two layers which have different velocity, and there is a velocity contrast between these boundary, and we also call the boundary interface. So this is my interface. And let's say that a P wave arriving at an angle. This is the angle. I usually measure it from the normal. This is the normal to this plane. This is a line perpendicular to the plane. A normal to the plane means perpendicular to the plane. It's normal to the plane. What happens to the wave? It will reflect. It will reflect, and the angle of reflection actually is similar to the angle of incident. This is the incident. The angle of reflection is always equal to the angle of incident reflection. It's reflected back, but there's going to be some refraction too. The wave will go to the second layer. Would it go straight or would it deflect? It will deflect. And how much it deflects, it's actually governed by Snell's law, a law called Snell's law. The time, the P wave, this is a P wave arriving to this interface. The time it hits this interface, some part of P wave will also convert it to S wave. That's something we call mood conversion. That's what we call mood conversion. P wave changed, part of it changed to S wave. And mode conversion happens only when the wave hitting the interface at an oblique angle. What's an oblique angle? An angle which is not equal to 90 or 0, sorry. The angle which is not equal to 0. What's gonna be then? That's the wave. If it's arriving like that, the P wave is P wave. It will reflect and go inside to the second layer without deflection. At oblique angle, at what you see here, we'll have a refraction, something called refraction. Going to be refracting to the second layer with a different angle than the incident angle. This angle is different than the incident angle. And it will also generate S wave. So this is a refracted S wave and also reflected S wave. Reflected P wave. It all depends on Snell's law. You might ask why there is mode conversion. I will not will not come to the exam because it's not mentioned in the book too, but it happens because the wave is hitting this interface at an angle. It's coming this direction. So whenever there is something hitting something at oblique angle, part of the energy go into this direction and part go down direction. So that will create a different wave types. That wave type is also S. And there is a principle called Huygens principle. I will not cover it right now because students will take it in other courses in seismic methods. But the Huygens principle, it allows that the mode conversion happens. So there is a mode conversion. For you, there is a mode conversion at an oblique angle. At normal angle, when the wave is hitting the interface at a normal angle, there is no mode conversion. And how they worked out all of these variables, for example, where is my, change this one. So how they worked out these values. So they have been worked out, you'll find similar to things in exam. So if I have an incident angle of 40, and the velocity of first layer and second layer, P and S waves, both P and S waves. I need to work out what are actually the refracted P, refracted S wave, reflected P, and the reflected S waves. If you know, for example, the incident angle and you know the velocity of P and S of the respective layers, you can work out easily the angles, refracted and reflected angles using Snell's law. And what's Snell's law? Snell's law is basically this law. So V1 is velocity of upper layer, V2 is velocity of second layer. You need to know these velocities and you know the angle of incidence. That's the angle of incidence. You need to work out then what's the angle of refraction. You need to work out what's the angle of refraction. So if I ask you, if the angle of incidence is 37 and velocity of first layer is 4 kilometers per second, what is the angle of reflection? Let's ask Malik Salti. Malik, what's the angle of reflection? Reflection. If the angle of incidence is 37 and the velocity of
37.
Huh?
37 sine something. Sine the difference in velocity.
No, it's 37. It's 37, exactly. The angle
But
of it's 37. Why? Because I again can use Snell's law. I'm first layer V1. Reflection is in the first layer, which is V1. Sine theta 1, I know it. sine theta 2, that sine theta 2, which is the thing I'm required to answer or give. These two are equal, they can be cancelled. Sine theta 1, sine theta 2 are equal to each other. So theta 1 is also equal to theta 2. And why there is a deflection? Why there is a deflection? Why the ray deflect? All the waves actually deflect whenever there is a property change. Seismic waves, light you'll find deflecting when it's moving from air to water. Electromagnetic waves, water waves even. Any wave type will deflect whenever it moves from one layer to another layer. But to simplify it for you, let me try to do some simple explanation. Start a new. I'm trying to create a whiteboard. You. So let's assume that there is something called like a layer. Let me get this pen. This is a layer. And let's assume a car is moving. A car, which is this car, it has 4 tires. 1, 2, 3, 4. At certain time, the car was here. And the car is moving like that. It reached this point. It reached this point where the first tire is here, this tire is here, and so on. So these 4 tires, the car moved at a certain time to this point. So what happens to this tire? Will it move? Because this layer right now, the second place, this is one place, this place, you can, this is, for example, let's say mud. And this is asphalt. This is mud. In the mud, even if you are pressing with the same, the accelerometer or pedometer with the same amount of energy, by default, your car might go faster in the asphalt. If this goes with the same speed, this goes from here to here with the same speed, in a straight line, with the same speed, with higher speed, the speed in here, let's say 5 kilometers per hour. In here, it's 20 kilometers per hour. So if you go with higher speed, but straight line in here, whereas this tire is still at 5 kilometers, this is not possible. This tire will blow apart. This tire will blow apart. Because how fast it can travel, it cannot go with the same speed as 20. In here, cannot go large distance. So I have this distance. This distance supposed to be, it should travel a smaller distance in here. Smaller distance, try to deflect toward, away from the normal. That's the normal. Try to deflect away from the normal with higher speed, but shorter distance. Travel shorter distance for this one to travel a higher distance. Is that clear? Oh, sorry, the opposite. I'm wrong. So this one travels a higher distance, whereas this one travels a shorter distance within the same period of time. Otherwise, the tire will blow apart. This travels a higher distance, 20 kilometers. This travels a lower distance, while its speed is lower within the same time. The time is the same. The speed is different. The speed is higher, so it travels a higher distance, whereas this one traveled a lower distance. So this is actually what you will.
The difference in distance, but the same time.
The difference in distance is a distance. It's not in terms of time. Did you switch off your micro? The distance, the difference in distance is different in actual distance. It's not. There is no difference in time. This actual distance difference. Where is it? This lost it somewhere. This distance, the actual is actual distance, real distance in terms of meters. But the time travel, the time is the same. It's the same car. This traveled faster, larger distance. This traveled shorter distance.
Another question.
Go ahead.
Reflection is only when we talk about the angles. I mean, if there is no change in theta, then it's not a refraction.
Reflection, yes. Reflection, the angle of incidence and the angle of reflection is the same. Always, that's true. Whereas for refraction, that's different. Refraction, we also call it transmission, because then we'll study something called critical refraction. Critical refraction. This is totally different subject. We'll come back to this critical refraction. There is refraction, but there is critical refraction. It's whole subject, critical refraction.
Okay, Doctor, last question. Sorry for too many questions.
No problem.
What is the relation between the reflection, refraction, and deflection? What is exactly deflection?
Deflection is simply the terminology I'm using in here to define that the wave is deflected away from the normal. It's not the same angle anymore. Refraction angle is not anymore the same as the incident one. Deflection is deflected. Haven't moved in the same direction. It's the same terminology, actually. I'm not changing anything. It's the same terminology. Deflection. It's deflected. This is also deflection. This is also deflection, but I'm saying it's deflected away. The refraction angle is not the same as the incident angle. That's my point. So deflection is the same as
Victor, you mean the change in direction?
Change in direction, yes. Let me ask you a question. If these two layers, this is limestone, this is sandstone, limestone, sandstone. If they both have the same velocity, what happens? What happens to the ray? Is it going to be deflected when it goes to the second layer?
No.
What do you say, Muhammad? No. As we said, in geophysics, there's supposed to be a contrast in physical property, which is in this case is the velocity. Even though there are two different layers, one is limestone, the other one is sandstone, or one is shale, the other one is limestone, geophysics cannot see that. Geophysics only see physical change in properties. If there is no physical change in property, geophysics is meaningless then. And it happens sometimes, but yet geophysics is very, very useful. It's used a lot. So there is, the wave will go straight if there is the velocity of both different, the geological layers are different. So maybe then you use different technique. Don't use seismic technique. Maybe limestone have more water content than, sorry, sandstone has more water content than the limestone. and then use electrical technique. Electrical detects electricity change or voltage or current changes. Might give you an insight. You'll find that two different layers in electromagnetic sense or electrical sense, not seismic sense. Is that clear? So here it's the same phenomenon as the way I explained. The wave is emanating in all the directions, and whenever there is an interface along which there is a change in the physical property, the ray will refract. The ray going to be refracting, and there is a deflection of the ray. It will not move in the same straight line, but it deflects either away or toward the normal. It depends on how the velocity changing from one layer to another layer. So the ray, there is a deflection or reflection. There is always a reflection, but what we see at the same time, the ray here traveled a longer distance than the ray in the lower or upper layer. Why is that? Because the velocity, for example, right now, velocity of the second layer is larger than the velocity of the first layer. So my question, could you prove that? Could you prove that this is larger distance than this one using these angles you are given in here? Try it yourself. If you cannot solve it, then ping me. And that's actually the Snell's law is the law we use to trace the geophones, to trace the ray, how the ray is moving through the layers. We know where it went actually. As geophysicists, we can tell which part of the earth it went through, what layers it covered. And usually this velocity, for example, this angle is equal to this angle. This angle here is equal to this angle. And so on. If I know the velocities of layers, I can trace how the ray have passed. So nowadays, what they do, they simulate this thing in computers. They give a lot of different possibilities. They say, oh, the velocities are blah, blah, blah. I have 4 layers and their velocity is like that. See how the ray goes. See how the ray goes. That's how you do it in the computer, because you can make this into computer thing, this Snell's law, and program it. And let's see how time it takes for the ray to go. And you compare these things to a real observation, to something you made in reality. You compare the travel times. Oh, my model giving me a different travel time than the reality. This concept takes me back to what we have studied already in the introduction, which is what? Modeling, forward and inverse modeling. What are they? This is a simple application of forward and inverse modeling. So whenever I say tracing the rays, I trace it in the computer. I see where it goes. I make a simple model of the earth. Oh, the earth is made of 4 layers. The velocity of each layer is like that. Not whole the earth, but part of it. Wherever you are interested in and wherever or when the place you are doing your investigation, geophysical investigation. So you set up your survey in the computer and compare your final results to the real results. See what goes, what happens. And this is how things are done in computer. So if the velocity is increasing as we go down, so what happens? At some point, there is something called turning depth, or the ray go back up. Why is that? Because if the velocity of the first layer is lower than the velocity of second layer, the ray will be deflected away from the normal. This angle is lower than this angle. This angle lower than this angle. This angle is lower than this angle. But these two are same. These two are same because of geometry. You see two parallel lines cut by a line, these two angles supposed to be the same. This we know already from school size, from the school long time ago. These two are parallel, these two are supposed to be the same. So that's how they trace actually the rays using Snell's law. And if the velocity is increasing with depth, the ray reaches a point where it returns, go back to the surface, and that point we call it the turning point. Since the Earth, the whole Earth, if I do tracing in the whole scale of the Earth is not parallel, is not a flat, but actually is eccentric, it's having a sphere shape. In this case, no more this angle is equal to this angle. This angle is not equal to this angle anymore if I use Snell's law. Snell's law actually gonna not be applicable for ray tracing. How I can determine what's this velocity then? Oh, sorry, what's this angle? I cannot determine because they are not parallel. To make again the Snell's law applicable even for spherical Earth, we use something called ray parameter. We use something called ray parameter. So this gonna be equal to this if I put these things. Let me rewrite this equation myself so you understand what I say. What is this one from here to here? From here up to the first one, I call this one R1, but this is R2. That's R3. So my signs are actually that, like that. Sine theta. What's this theta? Let's say it's theta 2. This theta over V. That's V2 equal sine this theta. This one. Or let's make it I2 dash. This is eraser. This is I2 without dash. This is V2 and this is V3. Oh, there is V3. I cannot make it black.
دكتور
V2 and this is V3. So how I make these two equal?
دكتور
Yeah. Go ahead.
if there is a 3R not 2 if I want to measure R3 and
So
we
let me
are in the example given R1 and R2, how will we measure the R3? Measure the R3.
I got your question. I will answer you. So this is R2. This is R. You need to put these two R3. Otherwise, this is not equal. So he's asking how we determine the R's. Is that your question, Muhammad?
Yes.
So how we determine?
Here in the law, we compare with 2R, not 3R.
No, we compare it. I'm ignoring this sign. This is right. What I'm writing in here is perfect. So in here, I'm comparing it with this one with this one. This part with this part using this equation. V1, V2. But here I'm using this one, this this one, this and this. This one, it's applicable to this case between the here and here. This is equal to this. Sine 1, which is this one, theta 1, is theta 2. They are not equal. They are not equal because the Earth is not parallel. To make this equation equal, we need to insert R1, which is this one, and we need to insert R2, which is this one. That's R2. If we need to apply the same thing to these two cases, these two angles, I2 and I2 dash, I need to apply this one, V2, V3, R2, R3. I1, I2, this angle is not equal to this angle. Whereas in this case, in the previous case, they are equal because the Earth, in this case, we assume that it's flat. But in reality, it's not flat. But for small scale surveys, you ignore. For small surveys, we ignore that the Earth is not flat. We assume it's flat because the angle difference actually is meaningless. It's very small. Is that clear to all of you? That's what is explained in here. Do you have any ambiguity with what I said? Let me move because I think with this rate, I cannot even give you the lab part, or maybe I give you half of it. So in real Earth, actually, we say the velocity is, if the Earth is made up of different layers, and that's how we make up the velocity. So each layer has a velocity, and the velocity is increasing. And that's how we measure it. This is the epicentral distance, and that's the time, arrival times. This is the arrival time, and we there are many different geophones or instruments or seismometers recording the arrival times, and we connect them along a line. The first onset of P wave, for example. If you want to measure then the velocity of certain layer, for example, you need to draw a line. So this line, the reciprocal of this line gives you the velocity. This is the distance. This is the distance. This is the time. Distance, time. And we know the slope is what? Farq. Change in time over change in distance. But that's the opposite of velocity. So you need to get the reciprocal difference in time over distance, difference in time. Distance over time gives you velocity. And this is how the ray travels actually in the air. They go like that and return back to the surface. The deeper they go, the deeper the farther away they travel. The Earth, as we know, this is the model, accepted model of the Earth. After studying many earthquakes, after recording the travel times from a lot of earthquakes, so they came to an agreement, all the scientists, that the Earth is made of these layers, which are the crust, the mantle, the inner core, and the outer core. And I think the outer core is liquid. And that's the reason if we see what's the P wave, the S wave, we see it goes to 0. Whereas the P wave decreases in the outer core. And they appear back in the inner core. So this is the accepted velocity models of P and E and S for the Earth, based on what they made up or assume the Earth is. It's accepted by geophysicists, geologists, and many different scientists. and whole the community around the world, not necessarily scientists. So they agree that the Earth is made up of different layers, and the main layers are crust, mantle, inner core, and outer core. They actually discovered this model using earthquake seismology data and calculating the travel time and using the Snell's law to see how the ray travels, which part it goes. So they were updating it, always keep updating it. Hundreds of times, many different peoples were using it again and again, and they find that the model they produced of the Earth is actually matching the real observations. The observations they get from earthquakes, travel times, real travel times from the earthquake. What's the real travel time? If I'm sitting in Oman and there was an earthquake, for example, in Japan, how long it takes, how much time it takes for the P wave to arrive to my station in Oman? How much S wave takes of time to arrive to this station? So I need a velocity. I already have the travel time. I can use the Snell's law. If I plug in these numbers to what models I have, I get the actual or very similar travel times. I get very similar travel times as is the observed one, as is or are the actual one, the one I'm reading from instrument, and I'm comparing them to the model. Yeah, the Earth is not perfectly like that. So there are some discrepancies, but for large scale, who cares about small changes? We cannot make it very, very accurate as is the case of microscope. We can make it simplified model, and this is accepted simplified model of the Earth. So there is no shear wave in the outer core because the outer core is made of liquid. And how they discovered this actually? How they found that there is no the outer core is liquid? It's because of what we know as phases. So if S is my earthquake, it happens somewhere here in the crust. The first wave which goes directly from source to some station here, let me change it to red. They call it this station, they call it P. If it hits here without any station, if there is no station, if it hits this place and go back and get recorded in a station here, we call it PP. It hits here, again go back here, and being recorded here, we call it PPP 3 times. As we said, there is a mood conversion. Mood conversion, P is changing to S. Whenever there is a change in velocity, there is a mood conversion. So P changed to S. This is a mood conversion. In here, we call it PS, PS. This is P, P, P. If it goes to the core mantle boundary and go inside the core, I call it P. It went as a P, went inside the core, inside the core, and returned back as P, PKP. This is a PKP. It went inside the core. Either outer or inner core does not matter. It went inside the core. If it reflects back from the core, we call it PC, P sub CP. Originated as P, hit the outer core and returned back and recorded at this station as P. If it's recorded as S, I know it came as P and recorded as S, but it hit the outer core. These things, we call them phases. And those are the most famous phases. There are many different phases. So how they know that there is an outer core? Because there is no S wave recorded from this zone from 89 or 98, sorry, I'm reading Arabic, 98 up to 180. There is no S wave at all. Why is that? Because the S wave cannot go in liquid. It cannot go in liquid. So it will not come as a direct S wave. It can come as a mood conversion. يعني P wave hit this part after coming out of a core, outer core. It can change its moods and appear as S, but that's not a primary. It's not a real S. It was mood converted S. Real S will not appear again here after 98. What about P wave? P waves. There is a P wave shadow zone from 98 to 1400. Oh, sorry, 144. 144. This is P wave shadow zone. There is no P wave in this zone. P will never ever show in this zone. Primary P wave. This P wave is appearing, but this is not primary P wave. P wave. P wave. That's P. This is P. This is P. Double P, and this is triple P. 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 This is not a direct P. It went deflected back from the surface and will appear usually very late than the direct P, if it was the direct P. So there is no direct P in this P wave shadow zone. And there is no S wave in this S wave shadow zone. I hope that's clear. So that's how is it. That's how they discover that there is inner core and outer core. And the P wave, why there is no P wave after 144 or within this range from 98 up to 144? Because this layer, okay, this layer mantle is of higher velocity than the outer core, higher P wave velocity. So if I draw this one, V1, V2, this one, V1 is way higher velocity than V2, and an incident P wave is arriving. This is the normal.
Well, it will reflect it.
It will be reflected, but is it going to be reflected away or toward the normal? It will be
Away.
reflected. No, toward. It will be reflected toward the normal. This angle is smaller than this angle. If V1 is higher, larger than the V2. That's what I said somewhere, I think, here. V2, if V2 greater than V1, the ray refracts away from the interface, from the normal. In the converse, the ray reflects toward the normal. So in this case, it's reflecting toward the normal, which is this line. And that's exactly what's happening in here. So let me draw it for you to see yourself. Which angle you think is larger? This one or this one? 1 or 2? Which angle is larger?
2.
Ahmed?
2. I
Mariam?
said 2.
2 is larger? Yeah, Hamed is right. 1 is larger. Why? Because velocity of the outer core is lower. P wave of the outer core is lower than the P wave of the mantle. So this one deflects toward the normal. It refracts toward the normal, whereas this is larger. So that's what happens. There is no, this is the angle, it arrives here, it deflects in this direction. It deflects, so this is the normal. This angle is smaller than this big angle, because it's deflecting toward the normal and nothing appearing. Nothing appearing in this P wave shadow zone. So if you ask me why there is P wave shadow zone, that's the reason. Because the velocity P wave velocity of the outer core is way lower than the velocity P wave velocity of the mantle. And according to Snell's law, there is a deflection toward the normal going from high velocity to low velocity. The high velocity, which is mantle, and the low velocity, which is the outer core. P wave. S wave, there is zero S wave velocity in the outer core. So there is no S waves at all. It's a total shadow zone for S wave, which is from 98 up to 180. P wave arrives after this one because of this, the phenomenon or the reasoning I just described. So keep these things in mind. This is because there is a very large velocity decrease across the core mantle boundary. Snell's law predicts the wave will refract toward the normal. This refraction creates a shadow zone, P wave shadow zone, for both P and S waves. Yeah. No direct P wave. The S wave shadow zone is from 98 up to 180. And this is what usually we record. So if you have this is your source, you have your station here, this is the waveform you get. There is no big separation. You cannot decide where exactly are P and S, because P wave is still coming, still recording. We are recording the P wave. Within the P wave, there is S wave. Similar to if I hit you and you're in coma, a different guy came and hit you. You're still in coma. Oh, who hit me? Where is the second one? Who second one who hit me? But if I hit you and after some minutes you got your mind back, you recognize who you are. Oh, you keep knowing that if second person hits you, oh, I was hit by a second person now. But if they are hitting you the same time, you does not recognize who is actually hitting me. Is it a P wave or S wave? Because they are happening, they are within very short time. Why it's very short time? Because the distance is very short. The wave haven't passed long distance to get or to make a segregation between the two, the P or S. So this is how you see them, the P wave, that's the one. It's always the first to arrive. You see, it's not just a single line, it's a train of waves. Then comes PP, then comes PKP. S wave is there. That's the S wave. There is no
Doctor, what kind of question can come in the same eye?
Again, Muhammad, what's your question?
What kind of question can come for the same eye?
I'm not sure, but you know, I cannot hear you. I'm sorry about that, but it seems that there is. Could you write it or say it in very slow way? Again, Muhammad, the floor is to you. Ask me. Hello? Can you hear me?
Yes, I think he's asking about the questions which can make him for this part.
What kind of question can come from this image? Yeah. I'm actually not sure. I haven't made a question yet for the exams or for the quizzes too. I haven't prepared for the next quiz yet. But I can give you all the exam quiz papers, but let me see with the course modules admins, because I lost my course module last year for the last semester, and usually I write all the questions there. I'm happy to give you those questions for review. I was actually searching for them. For this one, probably what's P wave shadow zone, what is S wave shadow zone, or maybe what is, for example, why there is why I cannot determine the S wave precisely in this zone, for example. What's the reason? That's something I explained right now.
دكتور بالعربي بتكلم كيف تربط بين هذا يعني سيزموجرام مع الشكل في الكرة الأرضية؟ هل هو يعني انحرف في المسار أو كذا يعني من خلال الشكل؟
Do you mean the shape of these seismograms without seeing the earth itself?
Yes.
Yeah, that's a good question. The things we consider here are the faces. So these are the faces, actually. And picking these faces, knowing exactly the faces is not an easy task. Geophysicists, they spend a lot of time determining what faces are. And why we need then three geophone or three sensors in the same geophone? They use techniques because P wave have different motion. If you have three geophones, you can determine the sense of motion. Is it moving like that, or is it moving? In what sense it's moving? So if you receive a P wave here early one, you can make a guess that this is a P wave arrived to me. The arrival of these P waves will tell you the velocity structure of the Earth, basically. And this is something I'm really interested on. So if I'm not knowing the Earth, if I'm assuming the Earth internal structure is not recognized up to this point, those travel time or these waveforms will be helpful to make a model of the Earth, to come up with a physical model of the Earth in terms of seismic waves. Seismic waves, because those are just travel times. And I keep
زين
update.
دكتور هل هذا تجربة حقيقية؟
This one?
ولا
Yeah.
إنه شكل توضيح فقط؟
No, this is real things. They might have been simplified. There was a slide, I removed it. I can show it to you. Let me check. Seismology. This is the real thing you see. Do you see this one?
Yes.
So actually, this is the one you see. So what you are, as a geophysicist, are asked to make, you go pick these traces. Oh, this is my first P wave. These are the P wave, probably.
Not easy.
Easy. Not easy. Okay, I picked the P wave. Oh, these are the surface waves arriving in here. They're showing as high amplitude with low frequency. Where is the S wave? Let me get the S wave. It's not easy task. This thing, as you see it in here, is this card is similar to what you see actually here, but it's simplified. Where is my mouse? Similar to what you see here. So it's not easy task. That's the reason I'm saying they use computer, there are a lot of publication in this regard, how to determine waves automatically even, not me get involved. Because why automatically? The seismograms around the world, they are continuously recording waveforms. Waveforms from airplanes, waveform from even tides. Earth tides are making waveforms. And those are recorded all the times. As I said, for earthquake seismology, I keep recording. Why I keep recording? Because I never know when an earthquake happens. So I need to record it. Whereas for seismic exploration, I have the control, I have the hammer, or I can determine when to make an explosion of dynamite or when to start vibrating with the vibroseis or vibrator. So I have the control on time. I start recording after I hit the ground. Actually, for the equipment we have in our department, we have a hammer. Inside the hammer, there is something called, forgot the name exactly, but the function it does is whenever I hit the hammer, it lets the recording starts. Pressure sensitive thing, whenever I hit the hammer, the recording will start too. So this is something a difference between earthquake seismology and exploration seismology. In the exploration seismology, we use the control source, vibroseis, dynamites. In refraction, the next chapter is refraction seismology. We'll study actually refraction. So I believe there is not much time left for the lab. That's somehow unfortunate, but I believe I give you the lab to do it yourself. What do you say? Is it fine? Or can we make it next week? Oh, let's make it next week. I don't want you to be angry on me. We'll make it next week, the lab. I stop here because just few, almost 20 minutes left for the lab. There are some explanations have to be done before doing the lab. So do you have any other questions? Because, there is one last slide left. So let's talk about tomography. Have you heard of tomography? Never ever. I recently went to the hospital and did a Ctc scan. Have you heard of CT scans? When they put you inside something, they do a scan, full body scan of you. I think you know that. They do it a lot in hospitals. Yes, they call it Ctc scan. يستخدم سماعة بلوتوث أن زعلك الصوت ضعيف من دون سماعة واضح. محمد شكيلي, I couldn't understand what you mean. I think I'm using the voice is clear, at least to me, whenever I rewatch my videos. Anyway, so we in geophysics use some similar technique. In CTC scans, they send a lot of sound waves through your body, hundreds of waves, and they get deflected back from your body and registered. They give an image of you. They record the time it reflects back. And finally, they observe an image of you. It's easy. Okay, no problem. Talking to Muhammad. So in geophysics, we use something similar, but Earth is bigger than a human body. A human body is small compared to Earth. So in case of human body, I can send hundreds of thousands of waves, sound waves. And that's also how they know what's the gender in mother's stomach and mother's belly before she gives birth. They send the waves, and they say, and knowing if she's a baby girl, it's harder. You cannot tell if she's baby girl except after like 4th or 5th month, but knowing if it's a boy, you can tell by week, not week, 2nd month or 3rd month, or from the day you get or the lady get pregnant. So they use the same technique. In earthquake, we are doing ray tracing. We are doing a lot of, we are having a lot of geophones and a lot of sources. The sources are usually in earthquake, big picture are the earthquakes. But we are recording this earthquake using hundreds or thousands of stations located in different areas of the world. In Oman, we have many stations in UAE, in Iran, and they are working usually in together. They have a lot of joint ventures between Oman, especially in terms of scientific research. In the Gulf itself, Oman and Iran and Oman, Turkey as well too. Turkey experienced a lot of earthquakes, so they have a good station array, a lot of stations in Turkey. So how I know if, for example, there is a body of high or low velocity within the rock? I need to send wave through this body from different directions. From here to here, from here, that's my body. But I need to image it to create a tomogram. Doing tomography, you need to record a lot of waves from all the directions, similar to the case we use for body scanning, Ctc scans for the body, or finding out what is the gender of the baby inside the mother's stomach. And we use actually ray tracing technique, which depends on Snell's law to see how the wave travels. It's not me who update the model. If I'm good in programming, I know how to deploy or convert these mathematics to equations or to formulas into the program, into the computer. Computer can easily modify the shape of this body, so my observed travel times are equal to the calculated travel times in the computer. Observed are the real one I recorded using my stations, and the calculated are actually the one made by computers. And the computer is giving me a model, is updating my model, is doing a change every time there is a change. And each change is actually an iteration. We name it in geophysics iterative process, as we studied in the previous chapter, what is inverse and forward modeling. So we are doing ray tracing. Ray tracing or tomography needs a lot of stations, a lot of sources. So here actually is a tomographic model of Turkey. So this is the line from Egypt. This is the Mediterranean Sea actually. This is the Red Sea you see. That's the Egypt. What they name this one? This peninsula? Sina, sorry. Yeah, that's Sina. Nile is not clear. But that's Turkey. And I have a line. This line is getting through it a cross section of the earth. So what I see a different plate subducting beneath Turkey. the velocity of this plate is different than the seismic velocities of these plates. The one I'm seeing in here is different than the seismic velocity of this plate. This is negative because the oceanic crust is thinner usually, is thick, is younger too, so its velocity is higher. It's high velocity, whereas this velocity is lower, and I'm seeing this is sinking below Turkey, and that's the reason there is a subduction zone. And from this subduction zone, I'm producing a lot of earthquakes. There are a lot of earthquakes in Turkey. Turkey suffered a lot from a lot of earthquakes. And most of the earthquakes, they happen along plate boundaries. Japan is actually close to a big plate boundary, and those plates are moving alongside each other at some rate. So the higher the rate, there is an accumulation of stress when two plates meet each other, and the stress increases to a point where those two plates cannot withstand the exceeded stress, and there is a break, there is a fracture, there is a movement along, or there is a fault. The fault is actually interpreted or manifested as a big earthquake, as seismic waves moving in each directions. And the stress is released. Anyone, if I, as a human, under stress at one point, I might cry. So Earth is doing the same. I might shout, oh, keep me alone, please. If there are some kids playing around, making noises, I might bear them for some time, but at some stage I will shout. So this is quite similar to what the Earth is doing. It cannot stand the more stresses coming on, and it fractures, it breaks. Geophysics, in geophysical analysis, we can tell the sense of motions, where the earthquake happens, exactly the location, the initiation point of this fault. And this is actually supposed to be the lab of today. First of all, determine the location of earthquake and also the sense of motion of earthquake. We have studied already the type of faults. We know that they are usually normal fault, reverse fault, oblique fault, transform faults. So how I can determine the fault created by an earthquake or produce an earthquake, a fault which produced an earthquake? How I can tell what type of fault is that? Geophysical analysis could tell you. On seismology, they use these techniques to determine the type of faults using an earthquake seismology data, the energy generated from earthquakes. So I think this is actually the last slide. This is actually a tomographic image of the Earth below Turkey. This is actually a 2D tomographic. This is 2D. Tomography can be done in 3D as we do with the human body. And but this is just simple one cross section. If you have a question, you can ask me right now. Otherwise, we'll leave the lab for the next week. I haven't thought that I spent all my time delivering today, just like I believe 15 or 14 slides, or even less. However, delivering few slides but speaking in good way, and you yourself understanding what I'm saying is also a plus point. Do you have any questions?
دكتور وش هذه القطعة هنا الدائرة داخل هذا بين الموجات؟ هنا فيها
Yeah, that's a good
شريط
question.
هذه.
Yes, what exactly is this? This is some anomaly. This is something different, having a different velocity structure or velocity value. We call it anomaly. For example, let's assume that this is a gold, pure gold somewhere in the earth. And you, as a geophysicist, are required to assess or characterize it, assess its dimension, its volume. What you gonna do? You do tomographic studies. You do a lot of
دكتور هل نستخدم الموجات لتحديد موقعها وإيش يعني؟
yes, we send waves, so the waves goes through them and return back. Then we use Snell's law to trace the wave where it moved using model. يعني we build a model, simple model, and every time the model gives me a different travel time than the actual one, I go update my model. Oh, I saw, okay, I think there is a gold. Let's assume my gold volume is that much. I assume it, but then, okay, I assumed my model is that. Let's do a model, and not a real one, in the computer. Oh, I know how Snell's law works. Let's see how much time it takes for the ray to travel from here to this geophone, this recording station. It has taken that much time, but I compare it to my real observation. I have already some real observation. In the reality, I had some source in here and station in here. So are they the same or not? Is my model, is the calculated travel time same to the observed one or not? If not, oh, maybe my model is wrong. Let me update it. Let me make some change. And you keep making changes until they match, until you guess it correctly. Oh, exactly, that's true. My observed and calculated times are the same. I cannot go into details how the ray tracing done and how we employ it in computers. Otherwise, that's a different course. That's a course who master degrees take it. I'm just giving you an idea. We use ray tracing based on Snell's law to make models of the ear. Is that clear? As I said,
Yes,
unique
دكتور. Thank you.
tomography is tracing, creating a velocity model. You will not create a real model, a velocity model. So maybe the velocity of waves in pure gold is different than the rocks, is faster in the rock. So in that sense, you make a model and try to compare your modeled results, observation, travel times from the model with the real one and see how much difference is there. That's what we call tomography or geophysical modeling, inverse and forward modeling. So this is anything with an anomaly, anything different than the surrounding, and try to find it. And that's what happened. If you have a stone in your, let's say, kidney, what happens? They scan you. They put some scanners in you. Stones will not let any sounds move through. All the sounds reflect back. But your body itself will act normally, except your bones, probably. But they will not, they know where the bones are. They know the shape of the bone. They don't know the shape of a stone. If stone will reflect any sound waves from your body, and they will find, oh, you have stones, and they can tell the size of the stones, how much stones you have in your kidney, and that's how they crack them apart. Yani. They shoot them. They not shoot them with some waves. They try to crack them in your body. They send a lot of waves to your body. The stone, what happens, because dense, it reflects all the energy back and the energy recorded. Whereas if there is no stone, they will go straight away without getting reflected back. In geophysics, we use something similar. We call it tomography. They call it imaging, Ctc Scan imaging. Is that clear? But yeah, by the end, my body is small thing. I can get a full tomographic model, whereas the Earth is really big. If you want to make it as clear as a human body, you need to plant a station every 10 meters. And every 10 meters on Oman, there is a seismic station, which is impossible. We have the maximum good broadband stations we have in Oman, they are 20 probably, or 16. 16, just 16, imagine. So how we can get the full image of Oman, seismic model of Oman? It's not very accurate because the number of stations I have, they are low. Is that clear?
Yes, Doctor.
Okay, so if everything is clear, I think I need to stop. And since I'm just giving a lecture, I don't need to give this lecture again. I just upload it for the next section to watch, whereas the lab will be postponed for the next week. That's fine. We're still with a pandemic. Not sure how to deliver exactly the lectures. And sometimes we go into difficulties. So let's see how it goes. So I make some modification in the module. Anyway, we'll have a quiz next week. Goodbye. Let me first of all stop recording.